Yeah, thank you, Stuart, and thank you for having me today. Good morning, ladies and gentlemen. It is indeed a great honor to have been invited to be one of the keynote speakers, and I've chosen a topic which is close to the research Ken Johnson was involved in. The title is Locomotive Wheel Tread Polygonization Caused by Torsional Axle Shaft Vibration. So I thought, let me start by recalling a few of the things relating to Ken Johnson. It is coming out of the work, the memoirs written by Roderick Smith. Roderick says the term contact mechanics is not precisely defined. That goes off. The term contact mechanics is not precisely defined, but we may sensibly think of it as a study of the phenomena associated with the interaction between solid bodies pressed or held in contact. It includes a knowledge of the contact stress field, a characterization of the material, response both plastically and elastically, deduction of the effects of surface roughness, of lubrication, of friction, and an understanding of the physics of the interaction forces between the surfaces. Ken Johnson has contributed to all of these aspects. It is sort of a statement which, again, shows the complexity which we have to deal with in contact mechanics. His major publications include topics in friction and wear, rheology and lubrication, rolling contact and adhesion. Important applications of his insights included the prediction of corrugations and cracks in railway lines. This brings me to corrugation on wheels, so we'll start with the presentation. The agenda for the presentation will be a problem statement, then a bit about the monitoring of polygonization, then excitation mechanisms. We've got two hypotheses which I want to go through, and the way forward. So where did it all begin? We heard complaints from the drivers of locomotives that for some locomotives there was a vibration which was a nuisance factor. And this occurred on our newer kind of AC traction locomotives. So we did ignore that initially because the complaints were not consistent, but eventually we realized that something is going wrong. Here we can see premature failure of some bogie components. Here the traction motor end shield lug failure. And we have got lateral stops. The bolts were missing here. And the primary spring failure here, not due to metallurgical or design factors, more for fatigue loading. And there were many other components. So the vibrations were sort of suspected that would shorten the life of the bogie components. So a comprehensive data analysis was done so that we could assess the situation. And eventually we realized that maybe it is out of round wheels which are causing these vibrations which we have been complaining about and where the fatigue failure has resulted from. So we had to do a few measurements. We took the locomotive into the underfloor wheel lathe, and we then put some displacement transducers in there and rotated the wheel and took the measurements. And the results were very, very distinct, a 20th order polygonization around these wheels. So that was very, very clear. So now we knew that when the wheels were out of round, and that is obviously causing the vibration. But the question is, what is the root cause? What is causing the wheels to go out of round? So about 2 years later, I'm standing in front of you and trying to present where we are today. But while we were researching into the root cause of this phenomena, we had to control the locomotive fleet by having regular measurements of out of roundness, identifying the worst locomotives and taking them to the workshops for reprofiling. So we use the standard weigh in motion wheel impact detector or WILD system as I've used in America to to measure the forces of passing wheels, and then we had an algorithm developed that could guide us in terms of the severity of the out-of-roundness. Here is an interesting graph from those monitoring results. We had the locomotive coming into an underfloor wheel lathe, and we can see the polygonization amplitude is very low, and then it stays like that, and then all of a sudden it shoots up, and this is where we then said, okay, locomotive must come in again for reprofiling so that we control it within what we could see acceptable levels. So this was a mitigating action while we were doing the research. The monitoring also showed very interesting phenomena. Here are two locomotives, locomotive A and B, and we see that locomotive B is having very few out-of-roundness exceedances. But the second locomotive, we can see, or locomotive A, we can see two different graphs here. And what we saw, that we have got a difference in the amplitude of the out-of-roundness depending whether that wheel is on the gear or the non-gear side of the bogie. So here we would have the non-gear and the gear side. So these have got lower amplitudes and the other ones higher. This is consistently through all the locomotive feet. So it gave us also a clue where to start searching for a possible solution. So we created some multi-body dynamic models so that we could possibly predict where this coupled mode, which we were seeing, is coming from. And if we can just click on the animation. So if you look carefully on this animation, you can see that the motor is going up and down in sort of a pitching mode around the axle. But what you also see is that the wheels are actually doing a torsional motion relative to one another. And if you look very closely, you will see the wheel on the non-gear side is actually having a torsional motion which is larger than the wheel on the gear side. So there's an unsymmetric torsional vibration in the locomotive. And it is this difference which we believe is causing then also the polygonization amplitude to be different between the two wheels of a wheel set. So having done these simulations, we then went ahead to prepare for some on-track tests. Here we can see we put an accelerometer on top of the motor nose suspension over there, and we had an axle shaft which we then instrumented for torsional strain. And with these two measurements, we were able to associate the coupled mode and the frequency involved. What was very important for these tests that we made sure that the wheels used during the test have got no polygonization, they're out of the box. And because we wanted to see the things that are happening behind the scenes and causing the torsion. So two hypotheses are presently being pursued. My two colleagues, Uri Spannenberg and Edward Reitman, have been spending a lot of time on them. The first hypothesis is torsional resonance of the axle due to self-excited stick-slip vibration under saturated adhesion. And the second hypothesis is torsional resonance of the axle due to forced excitation by the harmonics and interharmonics of the traction motor. I believe that we will be seeing that both are contributing to the eventual polygonization. So to go and the first hypothesis, self-excited stick vibration, we again started with a simulation model, and to determine the stick-slip vibration, and the difference, the model was created with a flexible wheel set, so we were trying to find if we can generate a difference in the adhesion conditions between the left and the right-hand wheel, and we did that while we were increasing the traction onto the wheel set in the model more and more. And what we found is that eventually, the wheel with adhesion conditions suitable for stick slip started self-excitation, and due to the negative damping, this loop was getting worse and worse. And we can see a distinct difference in behavior between the left and right-hand wheel, and we believe that that then started the torsional excitement of the axle shaft. So having done an analysis, we then again went back into on-track tests, and we set up the tests to be able to confirm some of these hypotheses. And the experimental results I'm showing here are for axial torsional vibration under saturated slipping on dry tangent track. Okay, so we start off by position A, having a low slip velocity. We right down on the stable part of the adhesion curve. And then as we increase the tractive effort of the locomotive, the slip velocity starts becoming at the point of maximum adhesion. So it wants to go over this little mountain there. And negative damping starts, and means torsional vibration starts to be excited, and it increases up to point C. At point C, the anti-slip device, which is part of the locomotive design, actually reduces the traction motor torque, takes it a bit off, and the reduction of the slip velocity follows. We're going back into the stable part, and it moves back to the stable part. So what we can see here, we've got the slip event of the axle itself as an axle, and the vibrations in that area is, on top of that, the torsional vibration of the axle. So both happen simultaneously, but it is the standard control algorithm which can then arrest and get rid of that slip event. So we come back into a stable positive damp situation. So the second scenario is when we look at the slip event with a wet tangent track. We remind ourselves of this very familiar curve. Here, if we've got dry rail, we've got higher instability, slope is a bit higher, and if we've got wet rail, we've got a lower instability. So what we see on the wet rail, as said, is a lower torsional vibration. We almost see no torsional vibration here. There is still a slip event, which is being dealt with the control system. So a different behavior depending on the conditions of the rail, wet or dry. Okay, in the third case, we have got a continuous slip event in a curve. Now we are going in a curve on dry track conditions. And what we're seeing here now is a continuous vibration. The anti-slip event of the control system is not doing anything. It seems to be excited continuously while going through this curve. And the question is, how do we arrest that kind of oscillation, which could be leading to polygonization? What we have realized through this research is that I can't rely on that screen, it just goes up and down. Basically what we're seeing here is that we have got a constant frequency with increasing speed up to about 45 kilometers an hour. The frequency is about 46 hertz. You will see that value coming in the next few slides as well. So self-excitation is as speed independent, and it stops here because beyond 40 kilometers an hour, more or less 45, the tractive effort of the locomotive gets reduced because it's starting to go faster and faster. So we're not running on the highest adhesion value anymore. Here is another graph just to show you what is happening in the test results. We look at slip velocity and the torsional vibration amplitude. And we can clearly see that the point of maximum adhesion is about there at 0.25 meters per second. And once we go beyond that, we get into the unstable negative damping area where we then have got increasing torsional vibration. So the experiments were quite clear in the phenomena which were happening. Eventually, the wave fixing was then due to the typical speed a locomotive travels while having this high adhesion value. It's always going up the hill more or less at 40 kilometers an hour because that's the balancing speed and the most powerful one. The second hypothesis comes with traction motor working. Here we look at what happens when we take the AC current and we convert it to DC and then back to AC again in driving these AC traction motors. The first thing which we do is we have got AC power coming from the overhead catenary, and that needs to then be rectified and filtered to an approximate constant DC voltage supply. This DC voltage supply, however, have distortions, as you can see here, from the rectification process. It's always an approximation. This DC supply is then taken and inverted back to a three-phase AC output for the variable frequency drive, which is basically then powering the traction motor. This variable frequency drive controls the frequency of the AC output and thus the motor speed. So this is the way it works. Now, due to this conversion and inversion process, the harmonics and interharmonics are created in the output of the variable frequency drive. The harmonics themselves are integer multiples of the inverter operating frequency, and the interharmonics are due to the modulation between switching function used to invert the DC supply to three-phase AC and also the DC link voltage. So it's all about the electronics and the frequency control of the AC traction motors. So let's look at two examples. The first one is forced excitation by harmonics. Remember the first one was the stick slip, which is created by itself in a way, but now we have got a forcing function working onto the axle shaft on a continuous basis. If we look at the harmonics, the test condition typically is on straight track, tangent track, going at 30 kilometers an hour below the maximum tractive effort value, and still having a high tractive effort. Then we get this kind of graph. Basically, it has got the frequency content over time. What we can see is all those blue lines are the fundamental harmonics. There's a green line, which is the gear mesh frequency, just out of interest. The speed is indicated down here, going to about 30 kilometers an hour, as I said. So, and this red line is the fundamental, the torsional mode, that 56, 58 hertz value is constant over there, coming from the traction motor. So what we get when we drive at these high adhesion conditions at that particular speed is that the second harmonic of the variable frequency drive starts interacting with the torsional mode, which we calculated for the axle and which was also related to the pitching of the motor. And we can see a bit of a darker area because the acceleration amplitude is going up in this particular area. So here we see very clearly a coupled resonance between the torsional mode and the second harmonic. So, and that activity is over that area. In the last 6 little spikes there, we can see very clear total slip events. So prior to that, it is not slipping yet, but it's got that force function going in there. The second example is torsional vibration caused by the interharmonics. Similar test conditions, but with slightly faster at 40 km an hour. Again, a similar graph. We can see now we're going at 40 km an hour. Here is our torsional mode again. And this time, as we said, we're looking at interharmonics. We can see there's a bit of a squiggle there. There are other graphs in the paper which will show you much more of the activities of the interharmonics. But here we can see that close to that torsional mode, the interharmonics also gets now excited. And the interharmonics can, under certain conditions, be almost like white noise. It's available everywhere, and it can talk to something which will resonate at a certain frequency. Okay, the wave fixing under the forced vibration is we can take the wheel radius, the vehicle speed, the torsional frequency, and by just looking at those calculations, we very easily see that it's a 20-order polygon, and in this instance, through the force excitation at 40, we get that coupled resonance frequency at 56 Hertz. So what is the way forward on this project? First, we've got some interventions which are related to the mechanical countermeasures. Reduction and adhesion deficiency, very difficult. Obviously, you could look at friction modification, maybe it would work. Reduction in the maximum tractive effort. It's not necessarily a good idea if we want to haul our long trains up the mountains. We might have to require another locomotive to do the job. And then we could also try to control it by just frequent wheel reprofiling. The focus, however, at the moment is on the electrical countermeasures, where we are trying to, together with the original equipment manufacturer, to modify the control system so that it can actually arrest and stop the torsional vibration, even though the total net slip of the axle doesn't occur yet. And then also the switching frequency which goes into the variable frequency drive when we are converting from the DC again to the AC. So these are things which I hope to be able to report back in the near future. And this brings me to the end of my presentation. Thank you for your attention.
Okay, thanks very much, Robert, for a very interesting presentation. Can I open it for questions, please? Sorry, Richard.
Thank you, Robert, for this really interesting presentation. One obvious question I have to ask, what's happening to the rail during these events? Did you look at this?
Obviously, the rail will also see the effect of these vibrations and these high forces. I don't even want to go there at this stage because we need to, that's why we're doing now, taking the locomotives out before they get the out of roundness goes totally out of control. That's the only thing we can do at the moment, and yeah, we're just waiting for some changes to the control systems, and hopefully it will work. We had indications already very positive, but we need a more robust solution that doesn't reduce our tractive effort, which we need.
Thank you.
Thank you very much for a very interesting and clear presentation, as always. Thank you for keeping tradition on that. Question on the measurements of wheel out of roundness. Are there any alarm limits or any regulations in South Africa on where really bad wheels must be removed?
Just repeat the last part. Are there any?
Wheel out of roundness on polygonization. Are there any regulations in South Africa when the really bad wheels must be removed?
Yeah, no, we don't have any particular regulation. We have at the moment, because this is only happening on our coal export line, we have put our own limit. there, as you saw on the one graph, and we're trying to control it within that limit. So once it goes over that, we flag it for maintenance. And we've been doing that for about 3 years, so that we are addressing the problem, sort of slowly trying to keep everything under control.
This is Xin Zhao speaking from Southwest Georgia University. I'm wondering, as I know that critical value for anti-slip systems is normally at 15 or 17%. Do you think it is possible if we reduce this critical value to a lower value will help this kind of problems, or is that possible to make a lower critical value for the anti-slipping system? Thank you.
Yeah, I think it's all about how the control system is developed and defined. Some of them just don't want to go over the peak of the adhesion curve. Others do go over and then try to control it, and others stay away from that. So we are working with that. As soon as we reduce the used adhesion value slightly, it helps quite a lot. But as I said, we need to keep the power in the locomotive at this stage, if we can. It's obviously a last resort to reduce the usable tractive effort so that we can control these force vibrations. That's where the trick comes in, whether it is force vibration plus the slipping.
Maxim?
Hello, Robert. I have one question for you. When you are talking about locomotives here, it's definitely, we can see influence of traction control system. But from your result, what you presented, do you consider only one type of locomotive, or you consider different types of locomotive which are in operation on your network? Because if it's one type of locomotive, it's high probability that you need to go to traction motor suspension system to check. If it happens with a lot of locomotives, different types, in this case it can be a problem with control system and electrical equipment.
Yeah, I think it's basically happening to one type of locomotive at the moment. Other types, that one graph compares a bit, and you can see they don't have this problem. We are very aware that the control system of this particular locomotive, especially when it does the switching, the choice of the frequency at which it does that would have an influence. So we're trying to find a solution in that without obviously changing any hardware. So if we can do it in electronic motor control software, that would be the first prize.
Andrea?
Robert, first I would like to ask you if I'm not wrong, some of the results you showed are about running and through curves at constant speed without traction, and the oscillations happen as well, so it is not a problem.
It's with traction.
Oh, okay, sorry, I misinterpreted your results. The question is, the 56 Hertz resonance that you showed is pretty low to be a second torsional natural frequency for the wheelset, which is something that Stewart also wrote about at the end of the 90s. So which eigenmode is associated to the 56 natural frequency?
It is basically the torsional mode.
First.
Yeah. And yeah, we were aware of, we were looking for the bending mode, but this is the only one that really pops up, and it couples with the motor nose pitching frequency, so then it gets sort of excited in the system. And then, in the simulation, prior to our on-track test, and then also during the on-track test, that frequency always just came up again. And the question is, where does it come from? Is it from the slip, or is it from the force vibration from the variable frequency drive?
I'll take prerogative here and ask a little question, and maybe it'll go on in the coffee break. I've been interested in characteristics of DC AC traction, not from this particularly, but for squats and studs and so on. What you've put up about the effects of that giving rise to little wheel slips might be relevant to that.
Yeah.
So it's a little thing to think about, because what you show is nice little slips happening because of the ripples on the DC traction.
When I started being involved in wheel interaction, I never thought I would have to read about AC traction.
Anyway, thanks very much, Robert, and I think we got a coffee break.